Hello and welcome to our talk. We are pleased to present our work HoloFusion towards photorealistic 3D generative modeling. This project has been supported by the EU-funded Prime ITN, Meta AI and UCL. Compared to the previous 3D-only HoloDiffusion approach, our proposed hybrid 3D-2D approach shows significant improvements in the generated sample quality. We now present our proposed method. Currently, the state-of-the-art 3D diffusion models are limited by sample quality. And while the 2D to 3D distillation-based methods have shown very good results, they still suffer from these geometric and appearance-based issues. To overcome these issues, we propose HoloFusion, which combines the best of both 3D and 2D diffusion approaches. The first stage of our method gives coarse 3D samples, while the second stage distills high-quality 3D view-consistent radiance field assets. The prior works related to ours include the 2D distillation approaches such as DreamFusion and Magic 3D. We note that there have been many more works in this space that have been proposed recently. More similar to ours, NerfDiff concurrently also proposes to use a hybrid 3D-2D approach in the context of novel view synthesis, whereas our main goal is a high-quality unconditional 3D generative model. Here is the full pipeline of the HoloFusion training algorithm. Let's go through this one step at a time. As a first step, we construct an approximate 3D feature voxel grid V-bar using the source views. Slightly different from the HoloDiffusion method, we concatenate these V-bar features with 3D noise for the first pass of the denoising instead of adding them together. This concatenation is then input to the base 3D diffusion network d-theta, which predicts the features for the clean and fully formed 3D feature grid V0, following which we render some target views in order to optimize the stage 1 photometric loss. The base 3D diffusion model is then augmented with a 2D diffusion model which super resolves the low resolution views rendered from the output of the base diffusion model. This brings us to the complete training pipeline. We call this first baseline HoloDiffusion star. Although the HoloDiffusion star samples look more detailed, the independently upsampled views of the low-resolution samples are 3D inconsistent and hence cause a lot of flickering in the 360-degree spin-around videos. As a first solution, we use a number of independently upsampled views to fit a high-resolution feature voxel grid using the mean squared error loss similar to NeRF. Although this pacifies the flickering a bit, this solution doesn't get rid of the flickering completely. The reason for this is that when upsampling the low-res rendered views, there can be multiple high-resolution hypotheses possible. We visualize the pixel-wise standard deviation for k equals 10 super-resolution hypotheses obtained from a single view in this figure. We then form the HoloFusion SDS baseline, which uses the score distillation sampling loss as proposed by DreamFusion to fit our high-resolution feature voxel grid instead of the mean squared error. Although the flickering is greatly reduced here, the SDS loss inhibits all high-frequency details and makes all the samples overly smooth and slightly off-colored. Thus, to overcome these issues, we propose a patch remix technique. In this technique, we obtain as few as k equals 5 super-resolution hypotheses for each low-resolution rendered views and optimize the loss only for the best matched one on a patch level. As apparent, our patch remix loss gets rid of most of the flickering while also preserving high-frequency details. Now let's take a look at the experiments in detail. These are the FID and KID scores to demonstrate the generative quality of our results. Our full method, last row, surpasses all the baselines in terms of the scores. Although Pygan gets better scores than ours on apples and donuts, its 3D agnostic training procedure doesn't produce 3D consistent samples. Here are some rendered samples visualized for qualitative comparison. Here are some more samples generated from our model to demonstrate the quality, diversity, and 3D view consistency. Finally, we cover some of the limitations and the future scope of our method. Due to being an optimization-based approach, our sampling process takes about 30 minutes. It would be interesting to research a method that doesn't require optimization for sampling. Secondly, our produced samples are in the form of implicit 3D radiance fields, which restricts their use in 3D rendering softwares. It would be interesting to extract clean meshes from our samples or to integrate differentiable meshing into our method directly. Please feel free to check out our project page by scanning the QR code. We thank you for your attention.